have your book open at the same time so you know what we're going over. Looking at section 19, which is sequences and series, which I think you do that partially in Algebra 2. I don't remember anymore. We used to do it in Algebra 2. I don't know if they do it anymore. She said she hated it, so I'm assuming you did sequences and series. Okay, so a couple of things we just need to kind of talk about what a sequence is versus what a series is. So by definition, a sequence, if you want it, so as we talk about them, you know the difference versus a series. A sequence is just a list of numbers, in essence. So for instance, could be 1, 2, 3, dot, dot, dot. That is a sequence of numbers. It's just you add one each time, whatever, you go to the next integer, however you want to think about it. That is a sequence of numbers. When you talk about a series is a sum of numbers. So that could be like 1 plus 2 plus 3 plus dot, dot, dot. So if you're adding up all of those numbers, then that is what we call a series. So we've got to make sure we know the difference between the two. It's just a basic definition, so that's no big deal. But we do have to know if I'm looking for a sequence of numbers or if I'm looking for a series or a sum of those numbers. Okay. Now, when we talk about a sequence of numbers, we usually write it in the form a sub n equals blank. N is what we call our index, basically. So for instance, we could have a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. All this relates to is what we call our general term. And it represents just the generic term. It could be anyone. So if I want to find the first term, the second term, the third term, the fourth term, the fifth term, that's what n would be. So for instance, if I put in here, I could put anything I want. Let's just say 2n plus 3. If that is my general term, that means I can find any term in the sequence I want. So if I want the third term, for instance, so the third term would be a sub 3. So what have I done when I wrote a sub 3 versus writing the general term? What's the difference? Don't all answer at once or anything.
What was the question?
What's the difference between writing the general term, the a sub n equals 2n plus 3, and then when I started to write out the third term, a sub 3? What did I do? Like, what's different?
You said n equals 3.
Exactly. All I did was say, well, n is equal to 3 for my third term. So in this case, if I have a general term, I do the same thing on the right-hand side.
So what is this section called?
Sequences and series.
Okay.
So if my general term, a sub n, which means n could be anything, it's a variable, it's our index is what we call it, is equal to 2 times n plus 3. Well, if I want my third term, I just plug in 3 for n, because n is now 3, and I solve. So what, 6, 9? Your sequence of numbers is made up of the terms a sub 1, a sub 2, a sub 3, not plus, dot, dot, dot. This is your sequence of numbers. So you have your first term, your second term, your third term, your fourth term, until we get to the very last term, which is our nth term, so a sub n. So we just keep going until we decide to stop n. So I could stop n at 5, I could stop n at 10, I could pick to never stop n. And that's where we have two different types of sequences. You have your finite sequence, and you have your infinite sequence. I'm going to hope that everybody knows the difference between the word finite and infinite. Okay. Nobody said yes or no.
Yes.
Yes.
So we all know the difference between finite and infinite, I'm assuming.
Yes.
Okay. So on, then what will be an example of what is finite, just to double check and make sure.
Like you set
Something that
restrictions for
ends.
n.
So both of those are very good explanations. So you set restrictions for n, or you can say n. The sequence ends. So that is both correct. So n could
Something
be
that has a limited.
very good. Yes. So it stops. Therefore, obviously infinite. So obviously, finite sequence examples of that could be like n equals 10, 20, etc. Anything we want. For an infinite sequence, n obviously equals infinity. In other words, it don't stop. And yes, I know that's improper grammar, but it don't stop. And that's how you tell the difference between your finite and your infinite series. Or, sorry, sequence. Okay, so hopefully that all makes sense. So we'll just start with the basic questions, and just to make sure we all get it and have the understanding here. Alright, so we're given a sub 1 equals negative 1 to the n. What was the other part of that? 2n. Things that they could very easily ask you are find the first four terms. So in this, really, honestly, most of the section is just about understanding what you're finding and making sure you find it. It's usually pretty easy, in my opinion. This is a relatively easy section. There's not a whole bunch of complicated math that goes on with it. So what does it mean to find the first four terms? Well, the first term is A1, second term is A2, third term is A3.
You don't do 0?
No, we don't start counting at 0. Depends on the book you're using and the things you're looking for. If we're talking about the first four terms, A1, it's the first term, 1 represents the first term. There will be some times when you do sequences in series where you do start at 0, so that is a thing. It just depends. If they just ask for the first four, it's 1, 2, 3, 4.
Okay.
Now, when they give you things, and when you get to higher math, most of you, the sophomores that are reaching Calc 2, will do a lot more with this in Calc 2, where we do start at 0 and different things like that. But the problem will tell you, and if it just says find the first four terms, that's 1, 2, 3, 4. Okay, so in this case, pretty easy because they gave us the general term. All you gotta do is plug in 1, plug in 2, plug in 3, and plug in 4. So 1 times 2 times 1, negative 1 squared, 2 times 2, negative 1 to the third, 2 times 3, and then negative 1 to the fourth, 2 times 4. So pretty generic, pretty easy. Like I said, this is not, the basics of this is you just got to be understanding of what we're talking about. So when I say like the general term or the nth term and things like that, we just have to figure kind of that out. So pretty easy to figure out here. So negative 1 to the first is negative 1 times 2, so it's negative 2. Negative 1 squared is 1, so then 4. Negative, skipping ahead myself. Negative 6, and then 8. At this point, when we do these things, a lot of what we do is we're looking for patterns. So this hopefully should be a relatively easy pattern. So what is the pattern for this sequence of numbers?
Counts by 2 and the ones that have n as an odd number are negative.
Okay. So all good things to point out. So very easily counts by 2. So you should be able to, at this point, start filling in the rest of them because this is a pretty easy one. The important part to note here, and what this question brings up, is the fact that, like Maddie said, we have the odd ones are negative, the even ones are positive. This has a name, and we call this an alternating. If I can spell properly, this is an alternating sequence. So anytime it alternates between positive and negative, every number, it can't be like positive, negative, negative, positive, negative, negative, or anything like that. It has to be positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, negative, positive. We call that an alternating sequence. Okay. Hopefully it makes sense, yes? Okay. Now, sometimes they don't give us our general term. Sometimes they just give us a sequence of numbers. And we kind of have to figure out and look for some patterns. So let's see, what was it? Just make sure. 0, 1, 4, 9. So in this case, they gave us the pattern 0, 1, 4, 9. We're looking to figure out. We're trying to find our general term. So in this case, we're not given a formula. We're looking for a sub n equals blah. Anybody see any patterns with those numbers that are in this sequence?
They're all perfect squares.
It's a very good thing to point out. Yes, that's something to look for. They're all perfect squares. How can we use that to write our general term, though? So in a lot of cases, what you want to write out is you want to write out the specific term. So a sub 1 equals 0. A sub 2 is 1. A sub 3 is 4. And then a sub 4 is 9. So write them out like that so you kind of get that pattern. We're looking for a connection between our n value and this value over here. So what's the connection between 1 and 0, 2 and 1, 3 and 4, 4 and 9? Maddie's already pointed out a very good pattern for us, and it's something we need to look for, is the perfect squares. So what I'm going to do is I'm actually going to rewrite all of these in this case into perfect squares. So we get 0 squared, 1 squared. Those two don't help us a whole lot. This is where it's really going to start to help us. 2 squared, 3 squared. Now do we see a different pattern than we do of just squares?
The n of the previous number is going to equal the answer, the one below it.
Okay.
Does that make sense? Probably not.
That makes 100% sense. So what she said is she found the pattern that this one squared goes here, this one squared goes here, this one squared goes here. So instead of saying it like that, though, we need to figure out how does this number relate to that number instead of the other way around. That's the only problem that we have with what you said there, Maddie, is that we have to figure out the pattern from the number we have to n, not n to the number we have, if that makes sense, hopefully. So how do I relate 0 to 1, 1 to 2, 2 to 3, 3 to 4? Should hopefully be a pretty easy pattern.
Subtraction.
So define subtraction.
Wait, what? Repeat that?
Somebody said subtraction, so I was asking them to define what they meant by subtraction.
Wait. I'm confused about the... Can you just pointed at them all. Can you do that again?
Yeah, so I'm asking how 0 relates to 1, how 1 relates to 2, 2 relates to 3, and 3 relates to 4.
Oh, the addition if you're going 0 to 1, 1 to 2,
Okay.
2 to 3, 3 to 4.
So Miss Abby is correct, in case you're not reading chat. So our 0
Oh.
is 1 less than our n value. So you gotta be careful on which way you're going, Madison. You're still going from this number we have to our n value. We want to go the other way around.
That's why
So
I said subtraction in the beginning, but then I confused myself.
that's fine. So how do I get from 1 to 0? So how is 0 related to 1? It's 1 less. How is 1 related to 2? It's 1 less. How is 2 related to 3? It's 1 less, etc., etc. So what we can say is this is now equal to 1 minus 1 squared. This is equal to 2 minus 1 squared. 3 minus 1 squared. And this is 4 minus 1 squared. So once we figure out that pattern, we can start writing this. Now, do you have to write this every single time? No. We're just going to be looking for those patterns. So the generic way is going to be that we have n minus 1 squared. Because this is my n value in each one of them. And each time I'm subtracting 1. The 1 subtraction part doesn't change. The squared part doesn't change. The part that changes is my first number.
We have to do this for this whole section. That's so hard.
The pattern recognition is something you will definitely need to be looking for, yes. It'll be just this, as far as, if I remember correctly, it's just this one section in the whole unit that you do the pattern recognition. The other stuff we do things with different, like summations and things like that. But yes, the pattern recognition, this is one of those things when we get to it, I always have to tell students very unfortunately, I can't tell you how to find patterns. That's one thing I cannot do. You have to be able to find them. Now I can give you tips and tricks and show you certain ones that you'll see a lot, like the squareds. So you should definitely, as soon as you see 0, 1, 4, 9, right off the bat, you should see that those are squareds. Okay? But other patterns, if it's a new pattern you've never seen before, it's sometimes very hard to figure that out. Okay? So now we're going to look at a second one, and I'll leave that one up. It was, make sure, 2, 6, 12, 20. 1/2, 1, 6. Okay, so now we have 1/2, 1/6, 1/12, 1/20. And again, we're looking for a pattern that connects all of those numbers. So again, I'm going to start with the same thing and try to see if I can figure out some sort of pattern by writing all of them out. So you get a sub 1, which is 1/2, a sub 2, which is 1/6, a sub 3, which is 1/12, and then a sub 4, which is, not 12, 20. And remember, our idea and our goal here is to get a connection between 1 and 2, 2 and 6, 3 and 12, 4 and 20 that is the same every single time. And yes, Ms. Abby, this is why most students don't like it. And in some cases, it may help also to write out other terms afterwards to kind of figure out that pattern. Sometimes it works, sometimes it doesn't. It just depends. But this is part of this is just pattern recognition.
So for the first one, we have a sub 1.
Mm-hmm.
To get the denominator, you multiply it times 2. And then for a sub 2, you multiply it times 3. And then a sub 3, you multiply it times 4.
Okay.
And a sub 4, you multiply times 5. So it's n plus 1, like.
Okay, so that's a good
something.
thing to start looking at. So what she's saying is she saw this was happening. So she saw that pattern of 2 can be 2 times 1, 6 can be 2 times 3, etc., etc. So what we're looking at this point is now can we get some sort of relationship between these two numbers, because these two match up. these two match up. So that's going to be our n value right there. The question is, do we have a relationship between this number and this number, this number and this number, this number and this number, this number and that number? And as I believe Miss Abby already pointed out in chat, we do. How is 1 related to 2, 2 related to 3, 3 related to 4, 4 related to 5, etc., etc.? No, you were right, sweetie. So what we should realize is if I'm trying to write my a sub n term, which I'm going to try to fit in over here, we have 1 over n times, if this is n, what is this one? Or what is this one? Or what is this one? How are they related to that previous number in that multiplication there?
Plus
So
1.
plus 1. So it's n, this number, times the next one, which is n plus 1. Does everybody see how that comes to be n and n plus 1?
Yeah.
Okay. So things you're looking for
Couldn't
because...
you-
Oh, go ahead, Harrison.
Couldn't you also just write that as n squared plus n as well?
Yes, if you want to write it out like that, that's perfectly fine. If you see that that's the pattern, there's nothing against that.
I figured that out, that type.
So yeah, if you figure out that way as well, there is no one way to do these problems. You've got to see the pattern and figure out how they relate. As long as they're equivalent, it doesn't matter which way you do it. So yes, that would work. Did I miss something when I wrote that down? Oh, I did. Oh, well. We'll talk about that later, Doris. So does that make sense, though, how you're just looking for the pattern? Again, tips and suggestions as you're taking notes, you should probably write down. Look for things like squares. Break numbers down into multiply. So like we did, like Madeline did here, where you did 2 is 2 times 1, 6 you could write as 3 times 2 or 2 times 3. If you break it down and look for those smaller things like that and realize that, oh, each of them have an n in it, and then we're multiplying it by the next number. So those are all ways you can try to break things down. Again, yes, I know this is pattern recognition and it sucks. Some of you are going to struggle with it. I'm not going to lie to you. It's a lot about practice, though. If you practice the problems that are in the book, you'll get a lot of different types and just get that experience. A lot of what this is, one of the reasons why I'm so good at it is I've seen these patterns before. Maybe not these specific ones, but I've looked for patterns for a long time since I've been doing math. So it's pretty easy to figure out what's going where. So it just takes practice, to be honest. It's not like we're going to give you some super hard, complicated one that you're not going to be able to solve. We tend to give things that you've seen before, something that's a little bit familiar, and sometimes something that may be a little bit of an extension. So for instance, instead of doing like, if I gave you a quiz problem or something, it could, instead of being n and n plus 1, it might be like n and n plus 2 or n plus 3 or something like that, to where it's similar, but maybe not exactly the same thing. So you always want to be kind of looking for those patterns of those numbers that connect to each other. Okay. Any questions on those two problems? Bye. Okay. So then the next thing that we're looking at is what's called a recursive sequence. Does anybody know what a recursive sequence is?
No.
Anybody in here had any kind of programming classes ever?
Yeah, but I don't remember. It was in 6th grade, so.
Yeah, okay. So anybody know, bonus point for anybody who knows this, what the Fibonacci sequence is?
I played the game.
You've played there's a game?
Yeah.
I'll have to look up and see what that is. So Kelvin says
It's
yes.
It's like the 2048 game on Cool Math Games.
I'll have to figure out. So Kelvin, what is the Fibonacci sequence then? I'll give you a bonus point if you can get this right. Okay, so do you just know the first numbers, or do you know what the Fibonacci sequence actually is? So very good, that is correct. I'm gonna hope you didn't Google that. Bonus point for you, sir. So the Fibonacci sequence, in case anybody does not know what it is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, dot, dot, dot. So that is the Fibonacci sequence. It was figured out by a famous mathematician. Obviously, his name is Fibonacci. That is his last name. I don't know his first name off the top of my head. The pattern here is that if I want to get the next number, I have to add the previous two terms. So I have to be given these. So these are given to us. These are the first and second terms. Some people call them the zero and the first term, doesn't matter, but they're the first two terms of the sequence. The next one is then got by adding the previous two terms. So 0 plus 1 is?
1.
Thank you. So you get 1, and then 1 plus 1 is? 2 plus 1 is? Etc., etc. Thank you for whoever's answering quietly. I appreciate that.
Me.
That's what I figured, but I didn't want to. I couldn't tell for 100%. So that's your Fibonacci sequence. That is an example of a recursive sequence. A recursive sequence is a sequence that, to get new terms, it relies on previous terms of some sort. Now, in this case of the Fibonacci sequence, it relies on the previous two terms. They don't all depend on the previous two terms. Sometimes they rely on just one term. Sometimes they rely on 3 terms. So that's what a recursive sequence is. Now, for any of you that decide that you maybe want to pursue computer programming or anything like that, recursive sequences are wildly expensive time-wise. Think about this. In the Fibonacci sequence, if I want the 20th term, what are you going to have to do?
Find the 18th and 19th.
So you're going to find the 18th and 19th. Well, how do you find the 18th and 19th?
You have to find all the ones before them.
You have to find all the ones before them. So while finding the 30th term, really not that bad. I mean, I've already got, what, 1, 2, 3, 4, 5, 6, 7, 8. I've already got like 10 up there. So, 30th, not too bad. But we talk about computer programming time, we're not talking about finding the 30th. We're talking about finding the 30th million or the 400th billion term or things like that. So in computing time, we want to say, okay, well, we need to make this quicker and simpler. Because in order to get to this, let's say the 30th term, I've got to do 28 calculations. Do you really want to do 28 calculations? No, I'd much rather do 1 or 2 if I can. So recursive sequences are very time expensive is what we call them. They're very hard to get further. So we always want to try to get rid of a recursive sequence. If you get into computer programming, that's one of the techniques they'll teach you, is if you can turn a recursive sequence like this into a non-recursive sequence. Those are things you look at. In this world, efficiency is king. If you can be efficient, you can save money. Think of it this way. Everybody likes your graphing calculators you use, right?
No.
Okay, except for I forgot. I really did. Okay, everybody but Madeline likes their graphing calculator. Now, what would you say if it took your calculator 30 seconds to do 2 plus 2? Would you then be willing to spend that kind of money on that calculator?
No.
No. I'm sure you've graphed all kinds of different things on your calculator. You see how quickly that line gets graphed? If you look at, like Madeline's, for instance, it's a lot slower because the calculator is slower. What happens if the computer takes 4 times as long to do something? Are you willing to spend the same amount of money on it? Calvin says if he can do 6 plus 7, he's willing to wait 30 seconds. Okay, but no. So and then think about it this way for any of you who do anything with computers, if you do computer gaming, programming, anything at all, if you're doing, let's say, I don't know, calculations on your computer, let's say 1,000,000 calculations, your computer can do that in milliseconds. But let's say, I don't know, 10 years ago, that would have taken a minute or so to do. Are you going to pay more for the one that takes a minute, or more for the one that takes a couple milliseconds and you have your answer immediately? So this is what
Depends on how broke you are.
depends on how broke you are. That's correct. I will say that. But that's what companies pay for. So now pretend you're a company that you're a multi-million-dollar company, and I come to you and I say, hey, I can cut your time in half. Are you willing to pay me for that? What happens if I cut your time in half? What are you able to do at that point? Well, you're either able to
Make
do
more.
one of two things. You can make more, you can double your productivity, you can have less people because it takes less time if you don't need to make more. Let's just say, so it only takes half the time. Well, you've just saved half your cost, your electricity cost, your pay cost for people, et cetera, et cetera. So I am saving you 50%. Or you're making more, so I'm doubling your profit. Wouldn't you say it's worth it to pay me quite a bit of money for that information? This is what computer companies do all day long. They look for quicker, more efficient ways. If you've ever played any kind of game, you'll notice that they have updates for the game. They do different things. They have better software that comes out every couple of years that has better graphics for that game, et cetera, et cetera. These are all things that they do because they found better and more efficient ways to code and to do these calculations. So that's one of the things that is very popular these days. Also, things like like your calculator companies. If I could find a better way to program the graphing calculator, I could take this to TI and make millions of dollars. So these are all things that are important to actual everyday use, and it's this pattern recognition and just kind of seeing what's going on. Okay, so when we look at recursive sequences, the difference between what we just did with just a generic sequence and finding the general term and your recursive sequences, they have to give you a starting point. So for instance, what we tend to write when we do these, so a sub n is a piecewise function, and just continue on with this one. So we get a sub 1 is -3, and then a sub, make sure I write it the same way they do. A sub n is equal to n times a n minus 1. So we have to be able to do at this point, because we want to write out the first few sequences, or first few numbers, so they want the first 5. We have to make sure we know what each piece is. So a sub 1, very easily given to us. What is a sub 1? But what is it?
The first term.
It's the first term. So if I want the first 5 terms, hey, there's the first one they gave it to me. So I've got part of my answer done right there. So a sub 1 is -3. I need to find a sub 2, a sub 3, a sub 4, and a sub 5. Well, how am I going to find those? Well, quite clearly it's going to be the bottom one, because the top one only gives me a sub 1. So in that bottom term, we have a sub n is equal to n a minus 1. Well, we should hopefully all know, what does a sub n stand for? A sub n is...
The generic term.
It's our generic term. So it represents any other term. Well, what does n represent? So on the right-hand side, equals. So n is...
Any term.
Okay, so
Any number.
n is the number term that we're on. Specifically, we would say it's the number term we're on. So if we're on like the third term, n is 3. If we're on the fourth term, n is 4. Well, here's the problem. What is a sub n minus 1? We got to make sure we understand what that is. So let's see, who am I going to call on? I like Brandon today. He's going to be my first victim. Brandon, what do you think a sub n minus 1 is? Oh, Brandon, don't let me down. Kelvin. All right, then I'll let your friend there bail you out there, Brandon. J-Dev, your turn. Help your buddy out so he doesn't get in trouble. N minus 1 is 0. How did you get 0, J-Dev? 1 minus 1. Okay, so I see that. Unfortunately, that is not correct. Let's have Dela. What is your idea on what n minus 1 is? Okay, so Dela says the previous term, which agrees with what Abby says above, and that's correct. So when we talk about things, we have to understand that a sub n is not just our general term, but it's also our current term. So a sub 1, we're looking for the first term. That's the first. 2 is n equals 2. That's the current term. We're looking for that term. So a sub n minus 1, if n is the current term, n minus 1 is our previous term. Because if I'm looking at a sub 2, well, what's 2 minus 1? 1. So that would be the previous term. Then in that case, what would a sub n minus 2 be then? Anybody can answer this one.
The previous term.
The previous term. So that would be 2 terms ago. So second term back. Or previous term works. So we have to make
Really?
sure we're understanding. Yeah, it's the same thing. So we have to understand what is in our formula. So when I read a sub n equals n a sub n minus 1, we can read this as the current term, which is a sub n, equals the term number, so n, times the previous term. So for a sub 2, what that looks like is it's 2 times a sub 2 minus 1. 3, go ahead and get rid of this one. 3 is 3 times a sub 3 minus 1, etc., down the line. 5. And at that point, what is a sub 2 minus 1? Well, 2 minus 1 is 1. So we get this is equal to 2 times a sub 1. This is 3 a sub 2. This is 4 a sub 3. This is 5 a sub 4. So if we notice, there's a very quick and easy pattern, is I'm multiplying n by the previous term. So it becomes hopefully very quick and easily understood that this is just 2 times negative 3, so we get negative 6. This is 3 times negative 6, which is negative 18. Then this is 4 times negative 18, 40, 64? No, 60. 72. Because I can math, I promise. Negative 72. And then 5 times negative 72, 350, 360. So negative 360. Yeah. Does everybody see how that works out?
That's very big, very fast.
It does get very big, very fast, which is why they only ask for like the first 5 terms. I don't know how much of this your calculators can do, to be honest, because we never really got to use calculators on it. There's certain things it can do. But I'm not sure exactly what it can do as far as finding like these values and things like that. There are ways you can do it to test and check and see. We may get into that if we have some time, but for right now, we just got to kind of know what the pattern is because it's honestly a really easy pattern, and you can do all the multiplications and things like that in your calculator, so you don't have to do them in your head. So it's not going to save you much time on these smaller scale things like this anyway. It would actually probably cost you more time to put it in the calculator and have the calculator do it than it would be just to do it on your own. Okay, does that make sense? Hopefully. All right, 1, 1. Okay. The next one in the book, if you're looking at the book, which I'm hoping most, if not all of you are, that's the Fibonacci sequence. So I'm not going to go over that one. It's almost the Fibonacci sequence. So they give you a sub 1 and a sub 2, and then they use n minus 2 and n minus 1. So it's pretty much the same thing there. Okay. And that will have to cut it for today. Pretty much that's class. Okay, so apparently it's in the book, so you can do some of this stuff with it. It's the sum and stuff like that. Yeah, we're gonna whatever. We'll do that later. So for homework tonight, you should be able to work on indicated term. Up through 21, it looks like. So that's about half the homework. So you can work through up through 21. A lot of them are pretty quick. It's just finding like the third term, the fourth term, the fifth term, the first 5 terms, things like that. So they're not going to take you very long. They're just asking you to plug in. Numbers 16 through 21 is asking you to find the generic term or general term. That's where they're going to have you write the formula. So 16 through 21 are probably going to be a little bit more difficult for most of you. Try to find that pattern. So please make sure you look at them, and I will be able to answer questions and kind of give you hints on those tomorrow. Everybody understand what we're working on today?
But we can't use the recursive.
Recursion, which is like,
Recursion.
yeah. So basically, they don't want you using the previous terms. You probably, for the most part, you would not get a recursive formula. The recursive formulas are a little bit harder to come up with in a lot of cases. So, like, they don't want to do like 3 times the previous term plus 1, because it could happen.
Okay.
But typically, it doesn't. Finding recursive formulas are usually a little bit harder, actually, than finding generic formulas. So usually, you don't come up with them.
It'll be like the first 2 that we did with the one with the fractions and the 0, 1, 4, 9, right?
Right. We tend not to ask you to find a recursive formula for most cases.
Okay.
So, yeah. It's something that's a little more difficult. So we don't do those. Okay, so again, just to make sure and reiterate, you were working on numbers 1 through 21. Most of them really honestly won't take you much time. Like, you could probably do the homework in like 20, 30 minutes, except for numbers 16 through 21 at most. Because 1 through 15 is super quick and easy. All right, you guys have a good rest of your day. If you have any questions, you know where I'm at.